I'm going to be talking about modularity and aesthetics today. So let's just get into it. So the first thing I want to talk about is why you should care about aesthetics and how your robot looks. And I think that there's generally a narrative that's pushed in FTC as well as other places of functionality over aesthetics. And while I agree that functionality should be a priority, I don't think that necessarily means that aesthetics aren't important. And the first place where I think that having a distinct look really sets your team apart is branding. So, for example, when you go to outreach events with your robot, your goal is to create impact and be memorable. So having a robot aesthetic that matches with your overall team brand definitely helps you achieve that goal. And my second point here is that aesthetic matters for awards and mainly the design award, which actually mentions aesthetic as well as your robot's appearance as criteria to win that award.
As a switch.
So, with that being said, we're going to talk a little bit about how a recognizable aesthetic is achieved. And I think the biggest thing here to keep in mind is consistency. And to that point, having consistency between how your robots look each year is incredibly important. So a team that I think does this really well is 8365 Gear Masters. And you'll notice that between the last 3 years, while their robot has changed a lot in terms of mechanisms, it still has very distinct elements like that orange polycarb, as well as the font on their numbers. And then another team I want to point out here is 112112 Clueless. And you'll see that even though they've had an even bigger change in terms of their robot structure, the one thing they've done a really good job at keeping consistent is their team color, which is that bright yellow that they use on all of their 3D prints. Now, the second part, and arguably the more important part, is having consistency within a single robot. So on the left, we have team 18219 primitive data. And I think one of the most striking elements about this robot is that they have all these hex pocketed plates, but more so the fact that all of their plates are pocketed in this style and they don't like switch it up or anything like that. And on the right is team 16379 Kooky Bots. And I think that like the most recognizable part about their robot is that black carbon fiber that surrounds the entire robot, as well as being used on a lot of their mechanisms. So now that we've talked about kind of what makes a strong aesthetic, we're going to cover what you can actually do in order to achieve that. And the 3 points here, which I'm going to talk about, I'll call the 3 Ps, which are pocketing, parallel plating, and printing. And I'm not going to cover just how these contribute to aesthetic, but also the functional purpose behind why we actually do these things. So to get started is pocketing. And put simply, that's just removing material from a part. More times than not, this is done on plates, but it's also done on things like 3D printed parts. And the main functionality behind this is to reduce the weight of any mechanisms, which is fairly self-explanatory because the more holes you have in a plate or given object, the less material you have, so the less it weighs. And the second reason behind why we pocket is to optimize for strength, because when we remove material from any given object, it'll always become weaker. So it's a constant balancing act between removing as much weight as possible while keeping the object structurally sound. And many teams do this by using finite element analysis on the object they want to pocket to identify where it's being stressed and maybe giving those areas more material. And now moving on to pocketing for aesthetics, the biggest tip here I can give here is, as I mentioned earlier, not only having a distinct pocketing pattern, some of which I've listed on this slide, but also being consistent with your pocketing. So using that same pocketing style for every plate on your robot. And so the 2 examples I have here for you guys on the left is team 18253 Beach Bots. And so they use more of like a freehand pocketing style. And on the right is 16236 Juice, whereas they use like a hexagon pocketing style. But again, they use all of these styles, or they use the same style on all of their plates. Now, the second thing we're going to talk about is parallel plating, which is basically exactly as the name says. It's stacking 2 plates parallel with each other. And for this, it might be helpful to see an image first. So up here, I have a picture of team 6165 MSET Cuttlefish. And if you look at their drive pods, which is what are what's enclosing their wheels around my mouse, you'll notice that their drive pods, are parallel. There's a plate on the outside and there's another plate on the inside. And the main functional reasons as to why we do this is mainly robustness. So in general, it's a good rule to support things like axles and standoffs on two axes rather than one. So by having a plate on the outside, we're able to do that effectively. And building off of that, another point for robustness is protection. So by covering the outside of our robot, that prevents other robots from hitting important parts of your robot that you might want to protect, like your wheels, hubs, or motors. Now, turning to the reason as to why we parallel plate for aesthetics. The big thing here is the ability to cover things that you don't want other people to see, like wires, while displaying things that you actually do want people to see. And generally, outer plates are a great place to put theming related things. So that includes like your team number, your sponsors, because your outer plates are going to be one of the first things that people see on your robot. And so as for our team, one thing we've started doing is a plate stack with our outer plates, which looks something like this and allows our outer plates to look kind of like turtle shells. And finally, I wanted to talk a little bit about printing. And what I mean by that is using accent colored 3D prints throughout your bot. And it really helps here to make those prints your team color. I'm not going to show any examples here just because we've seen a couple already. And our team actually has a resource that I'll share in a few minutes about 3D printing. So that being said, let's go ahead and jump into modularity. So once again, I'd like to answer the question of why you should care. The first reason would be in order to add new things to your robot. So sometimes you'll want to create new mechanisms that better adopt the meta or just mechanisms that help you achieve certain game challenges. And the second thing here is to change existing mechanisms. So if you want to get more performance out of certain subsystems or make them more efficient or reliable. And moving on, I actually want to address sort of like two different techniques as far as modularity goes. So one of the more common ways that teams approach this issue is designing their mechanisms one by one and building them one by one while making sure to have modularity in different ways to interface these together. Now, the second approach is to design their whole robot all in one go and add modularity after the fact. And this route is what our team typically chooses to take. And while adding modularity to these kinds of robots can be difficult, the main advantage is that you're able to see and visualize exactly what your robot will be before you build it. So it lets you do a lot more optimization in the design phase rather than the build phase. And so I actually wanted to revisit Team 11-12 Clueless here because they do a great job of taking the first approach of building each mechanism separately while retaining modularity. And they actually have a video on their YouTube channel detailing exactly how they did this on their Freight Frenzy robot. And I think it's a really good watch just because they talk about like all the things they did modularity wise in a lot of detail. But to highlight the one thing I really liked about their robot, they use a lot of these shower drain plates that match their build system. And in this picture, you'll see that their wall rollers as well as their scoring mechanism are both mounted on this top plate, which allows them to be really, really versatile in adding like whatever new mechanisms they want. And now we're actually going to talk about the second approach of about designing the whole robot beforehand and then adding modularity after. And being a team that goes this route, we found that it's a lot easier to add modularity by adapting existing holes on your robot using 3D printed mounts, as well as making sure those mounts are constrained properly, meaning like they won't move around or rotate. And for this part of the presentation, I'm going to go over the first robot that we built this season, which had a lot of issues that we had to fix, even though the bot didn't necessarily lend itself to being modular, so to speak. And just to give you guys an idea of what I'm going to be talking about, this is a top-down view of the robot that I'll be referencing. So this first example was our claw, and this was actually originally designed to be an active intake with servo-powered wheels. And you can actually see that being reflected with those bearing holes at the end of each of these plates right here. But what ended up happening is that the wheels didn't grip the cones as much as we would have liked. So we decided to switch it over to a normal claw. And we did this by using 3D printed claw pieces that fit around the standoffs that were used to hold the two plates together. The second example is another 3D printed part that was used for our crossbars. And what I really wanted to point out about this part is that there's actually only one screw that's holding it to the plate, which means in theory it should rotate. But if you look at the second picture here, there are actually 3D printed flanges that extend into the plate. So it's being prevented from rotating as it's like being braced against the aluminum of the plate. And I think this is a great example of what I mean when I say using constraints to your advantage, because even though there's only one screw, it's still being constrained like in every axis. And the final example I have is this other crossbar that also serves a couple of other purposes. The first of which is to integrate color distance sensors, and the second is a hard soft for our arm to rest on. And these three pieces, or these two pieces, were both 3D printed and mounted to this aluminum plate. So that's just another example of modularity. And so finally, I just have a couple resources. Uh, and then really you just, if you want to access any of these, just remember this link and then you can come to the last slide. But that's about it. So thank you. And I'll take any questions.
All right, thank you. Looks like we have a few questions online. Okay, so um, Adoye from team 21163 asks, should the team number be on both sides?
Yeah, so it's a requirement for your team number to be on both sides of your robot. Um, and pay attention to how your team number is displayed because it needs to be mirrored on the other side so that it's readable by referees.
All right. Second question, do you need a central control unit to manage and coordinate the modules, or will each module operate independently?
Um, okay, so I believe this question is asking is talking about robot subsystems. So I think you can go like either route. You can design each subsystem individually and then put them all together at the end, or you can design them like in parallel with each other, which is what our team does. I think either method, like each has its own merits. So depending on whatever you want to do, go for it.
All right. And last question from online, how you ensure that the modular components can be easily replaced or upgraded without disrupting the entire system?
Yeah. So I think the yeah, I think the biggest tip I can give here is to use like a 3D CAD software to actually check like the components you're putting in will fit and they won't like clip into any existing mechanisms. And I think that there are a lot of teams here today that'll talk about using CAD and stuff like that.
All right. That's all the questions we have online. Do we have any questions from in-person folks? No? All right. Well, that was Infinite Turtles. Thank you.
Thank you.